Yeah, thanks a lot, Max, for the nice introduction, and thanks a lot for the opportunity to present here. It is a great honor, and yeah, I would like to present a paper which is a collaborative effort of the people that you can see here. It is a project that took us a long time, so I think we started working on this 5 years ago, and it is about statistical reporting errors. So what is a statistical reporting error? In economics, we mostly have statistical results being presented in tables, and then we have coefficients with standard errors. And then additionally, we have some eye catchers so that yeah, people can easily infer whether it's significant at the 1, 5, or 10% level. And the typical statistical reporting error occurs when, for example, a result is labeled to be significant at the 5% level, but actually it should not be significant if we look at the coefficient and the standard error. So that might be just a honest mistake, or it might be the result of questionable research practices, such as rounding down p-values, for example. But either way, in the end, we have a paper that shows that the result is significant, which may mislead the reader in thinking that the result might be robust across specifications, for example, when it's actually not. I stumbled the first time up on reporting errors when I was actually part of a team of 15 PhD students. And we were actually interested in analyzing biases in economics, and we were coding a lot of coefficients and standard errors and eye catchers from regression tables. And it was my duty to check the quality of the data. So everybody was sending the data to me, and I thought it's a nice idea to check whether the coefficients and the standard errors are actually consistent with the eye catchers that the other co-workers coded. And this was in the evening, and I did this, and I was super shocked because about 30% of the articles had inconsistencies there, where the eye catchers were not fitting to the coefficients and standard errors. And yeah, I was very frustrated. And when I woke up in the morning and I actually looked at the exemplary papers, I saw that the coding was actually good, but that the mistakes were in the papers. And that was the point where I was getting interested in reporting errors. And only then I realized that this is already something that Michelle Merton and colleagues comprehensively assessed in psychology. Yeah, but in economics, it is a bit different to analyze, because in economics, we mostly report our results in tables. And this makes it much more difficult to actually gather the information from the tables. So a typical economics paper looks like this, where we have the different, mostly regression specifications in the different columns. And then the idea is to show robustness of, for example, variable 1 across different specifications. And when we look at this table, we can, for example, see that in parentheses, we have t-values. And the t-value here is 3.78. And it's labeled to be significant at the, it's labeled to be significant at the 5% level. So it has 2 stars here. But actually 3.78 is bigger than 2.58, which is a critical value. So this should actually have 3 stars. Maybe not a big deal because it's still significant. Here it's the other way around. It's labeled to be significant at the 1% level, but actually it's only significant to the 5% level. So 1.96 would be the critical value. And when we look, for example, at this value here, this is labeled to be significant at the 5% level. We can see that the t-value is only 0.77. So this is actually not significant at all. And this, of course, here constitutes a quite strong reporting error, because something that's not significant at all is actually labeled to be significant. So this brings us to 2 dimensions how we can define reporting errors. And so we have basically 4 definitions for the reporting errors. we can distinguish between overstated and understated reporting errors. So that means overstated if basically a result has more stars than the coefficient and the standard error suggests. And understated is the other way around. Something has less stars or asterisks or eye catches than actually the coefficient and the standard error suggest. And a strong reporting error means that actually statistical significance switches. So we can define a strong overstated reporting error to be a reporting error where the calculated p-value, so calculated means based on the coefficient and the standard error, suggests non-significance, but the eye catcher actually shows that there is a significant result. And understated is the other way around. So the calculated p-value suggests significance, but there's actually no eye catcher given. And a weak reporting error means just that there are more stars or less stars than actually eligible, but the result generally remains significant. So the calculated p-value suggests significance, but too many eye catches are given. This would be an overstated weak reporting error, and the calculated p-value suggests significance, but too few eye catches are given, would be an understated weak reporting error. So when we look at these definitions and apply them to the previous table, we can see this would be a weak understated reporting error, because this should be 3 stars and they give us 2. This is a weak overstated error. This should be 2 stars, but they give us 3. So we do not bother that much about weak reporting errors because they are not that much influencing what we read from the paper. What we care about are strong errors. So this would be a strong overstated reporting error, because here we have something that is clearly not significant being labeled as significant as a 5% level. And then we also have something that becomes a bit more tricky, because here we have a value that is labeled with a t-value of 1.7 to be significant at the 10% level. When we look at this at first sight, we think it's fine. 1.64 is a critical value. But actually, and I go back 2 slides for this, we can see the observations are only 20. So assuming we estimate only one parameter here, we have 19 degrees of freedoms. And so with 19 degrees of freedoms, the critical value of the t-distribution would be actually 1.73. So this is actually a strong overstated reporting error. So with our approach that we want to discuss here, we actually also need to gather the degrees of freedom from the tables. So StatCheck in psychology is very powerful to extract the statistical values from the papers. This is because in psychology, the main results are reported according to the APA guidelines in the text. In economics issues, we have tables, and the main results are not necessarily repeated in the text. And everybody is presenting the results in a more or less heterogeneous way. People report it with t-values, with p-values, with parentheses, without, with standard errors. So everything is possible. And the idea of this project is that we have an automated approach. And this automated approach is something we call DORIS. So DORIS stands for the Diagnosis of Reporting Errors in Scraped Tables. And what we did here is we crawled from the websites of the top 50 economic journals, all the PDFs and HTML articles. The idea here was to use regular expressions rather than machine learning, because the idea was that when we diagnose a paper to have a reporting error, we want to have a very low error margin. So this is why we ruled out machine learning in the beginning. I'm not sure whether I would do it again, but for this project, we did it completely with regular expressions. So we focused on the top 50 economic journals, and we focused on HTML documents because HTML allows us to easily identify tables in a document, which is not that easy and reliably done in PDFs. This reduces actually the journals to 32 journals because the remaining journals do not provide the articles in HTML. We have a time range from 1980 to 2016. Unfortunately, 2016, Germany, the German universities and Elsevier started a big fight, and all the access to Elsevier journals was cut for German universities. So this is why our data ends in 2016. And what we get from the tables is core information. So we have coefficients, standard errors, etc. And the redundant information, which means the eye catchers. So redundant in the sense that we can calculate significance based on the statistical test, coefficient with standard error. And of course, the eye catcher also gives us this information. We collect a lot of metadata, table nodes, and the whole article text. We look for clustered standard errors, nonlinear models, etc. Because all of this may influence how we diagnose reporting errors. The vast majority of tests is reported as coefficients with standard errors in economics, so 72%. So we developed DORIS in the following way. We use from Abel Brodeur and colleagues 360 tables, which they coded manually. From previous work of our group, we have 264 tables. And we also randomly selected 50 tables from the top 10 field journals in economics, giving us another 500 tables. So this results in more than 1,000 tables, and then we crafted the regular expressions in a way that DORIS gives us for each table reliably what the coefficient is, what the standard error is, what the p-value is, what the t-value is, and what the degrees of freedom. We then applied DORIS to the top 10 field journals in economics, and further improved DORIS by using 100 randomly selected tests. So basically, we looked here for some infant diseases and improved DORIS by this further. And then in the end, we evaluated DORIS by applying it to all journals and then selecting 100 tests randomly per journal. And DORIS supports discovery rate of roughly 1%, so it's 1.2%. So that means only in 1.2% of the cases, something was not correctly interpreted. So that brings us to the data sets. So we scraped 25,000 articles, and DORIS extracts tests in roughly 4,600 of them. So why this drop? This is because we have a lot of theoretical articles, and also papers start to use confidence intervals, which is something that DORIS is not yet able to detect. And also some authors in economics start to avoid eye catchers. So this explains this drop here. And then we extracted tests. But as I said, DORIS has a false discovery rate of 1%, which is nice. But for reporting errors, it's a problem because reporting errors themselves are a rare event. So we checked all of these tests manually, which was a major task to do, and corrected them. And then we came up with this data set here with roughly 4,000 tests. And then we removed some outliers. So what are outliers? For us, an outlier was if we have 100% reporting errors because the article says standard errors in parentheses, but it's actually t-values. And we thought that this is not something that we want to label as a reporting error because the reader can easily spot this and correct this in his or her head. We are more going for the reporting errors that are easy, that are not so easy to spot, where maybe 2 of 8 coefficients are only significant because of an eye catcher, and one believes that all 8 are significant, but actually it's not that robust as suggested. Then we also shrink to main tests. So we have all tests reported in the tables, and we look at main tests, and we define this as the first 3 rows in a table. Why are we doing this? We looked at the distribution of the Z values per row, and we saw that in the first row, we have a major discontinuity at 1.96. So indication of selective reporting for significant results. We also see it in the second row and in the third row, but in the fourth row, it's not that strong anymore. So we decided to define main tests as the first 3 rows, assuming that researchers selectively report significant results for the main tests. But we also have a robustness check only using the first row. So here are some descriptive analysis. This is the average amount of tests per article per year. So economics articles publish a huge amount of tests. Here we have roughly more than 150 tests on average per article. And we can see the steep increase of empirical articles in economics over time. So this is the main reporting errors result. I would like to focus here only on 2 numbers before going to the hypothesis testing part. I would like to focus here on the article level, and we can see that we have strong reporting errors for all tests in 30% of the articles, or 31% of the articles. So 31% of the economic articles have at least one strong reporting error, where a result is labeled to be significant when it's actually not, or the other way around. So it's not labeled to be significant when it actually is. When we focus on the main tests, we can see that this is about 15% of the articles. And this is in the same ballpark as was found in other disciplines. So then we were asking ourselves how important this is. So do we only have single or isolated reporting errors, which might be just an accident? Or is this something that from time to time happens quite frequently? So here we looked at the share of reporting errors per table to get an idea of how many reporting errors actually occur in one table. And we can see that the share is very small in many cases, but we do find also articles in which the share is actually quite high. And when we focus on the main test, we find a similar pattern. So there are also articles where reporting errors actually make quite a share of the regression table. Then we looked at some of these articles, and we indeed find a couple of instances where, when reading the article and looking at the inference and the conclusions of the articles, the conclusions actually are not valid anymore. We added anonymously these examples to the appendix of the working paper, so to strengthen our argument. Then a key point is to understand, why do overstated and understated reporting errors occur? Overstated reporting errors are very intuitive because they are consistent with the incentives in academic publishing. We want significant results, so it is quite easy to understand that there might be more eye catchers than actually the results suggest. But understated reporting errors is a bit strange because most of the time we do not want to report results that favor a null, at least most of the cases, but it's a very seldom case. So what we do is we think about the understated reporting errors as a benchmark for random errors or honest mistakes, and compare this to the overstated reporting errors. And we can see over time that this is not much different. This is for all tests. When we look at the main tests, we can see that actually indeed the overstated reporting errors exceed the understated reporting errors. So we interpret this as an indication for a systematic bias in the favor of significant results. This does not mean that this is questionable research practices or fraud. It could be also honest mistakes, because it might be much easier to spot that one forgot a star in the regression table compared to having a star and not checking it in depth, because having a star is always good, right? So this might be not necessarily reflecting questionable research practice. Okay, coming to the hypothesis testing part. So we pre-registered two hypotheses. The first one is that journal policies regarding the availability of data and software code are associated with the probability that a test is afflicted by a strong overstated reporting error and a strong understated reporting error. So the idea is that there's a lot of arguments that data and code availability policies are helpful in improving research quality, and we actually wanted to check this. The second one is the top 5 journals in economics. So in the economic research domain, there are 5 journals that are named the top 5. And they are very prestigious. So publishing in these journals helps a lot to advance the career. And we were interested in whether top 5 journals are also associated with strong overstated or understated reporting errors. There's some prior evidence that prestige of a journal might be related to the prevalence of reporting errors, and we wanted to test this here. It might be two ways. It might be that the research, the review process is so rigorous in these journals that there are no errors, or it might be that the incentive is so strong to get published in these journals that there might be actually more errors. Okay, so this is a regression table. So let's focus on the first 2 columns. This is a logistic regression for all tests. And we look at strong overstated errors. So this means dependent variable is 1 if there's a strong overstated reporting error and 0 otherwise. And then we have a dummy for data and code. So if the test was published in a journal with a data and code requirement, and whether it was published in a top 5 journal. These are odds ratios. So everything below 1 means it reduces the probability to observe a strong overstated reporting error. And we can see that the point estimate is consistently below 1. And it's significant at 10% level. That's the common threshold of significance in economics that is reported in parentheses. And then we correct for multiple hypothesis testing with a false discovery rate. This is reported in brackets. And then the effect here for the model. So the difference between these 2 models is that the first one has no controls and the second one has controls. So in the second model, once corrected for multiple hypothesis testing, it's not significant. If we look for strong understated reporting errors, we can see again, the coefficient is below 1, but it's not significant. For the top 5 journals, we see actually a positive effect here. So the coefficient is bigger than 1, but it's not significant. And for strong understated reporting errors, it's also not significant. This was a pre-registered analysis, and when we analyzed this data, we realized there's a much smarter way of actually analyzing this data, because this is a purely observational regression that we did. And the second thing that we did, which I'll show you on the next slide, is a difference in difference design, where the idea is that journal is considered to be treated if it has a data and code policy, and it's not treated if it does not have a data and code policy. And in a difference in difference design, which is a very popular quasi-experimental design in economics, basically one compares a pre-post in the treatment to the pre-post in the control group. The issue is that a standard difference in difference design was not applicable here because we have a staggered treatment. So that means that all the journals are not treated in the same year, but some journals are treated in 2008 with a data and code policy. Other journals are treated in 2016 or 2008. I said that 2012, for example. And it has been recently shown that difference in difference designs become biased then. But there's already a paper by Borusiak showing that the estimator, the imputation estimator, is suitable for a staggered diff and diff design, and we applied this estimator. And I would also like to focus on the first two columns. And we can see this is now an OLS estimate. So negative means it's reducing the prevalence of strong overstated reporting errors if there is a data and code policy active in the journal. And we can see the p-values here suggesting that it's statistically significant. And what is important in a difference in difference design is the pre-trend test, because in a difference in difference design, what we do is we assume that the trend of the control group is the trend of the treatment group in the absence of treatment. And therefore, we need to test for common trends before the treatment. And we can see that the test is not significant. So this is what we want, because it tells us that there is no indication that the trends are different. So this suggests a causal effect of data and code policy on the prevalence of strong overstated reporting errors. And we find a similar direction for strong understated reporting errors, but it's not significant. Then we looked for robustness for anticipation, because data and code policies might be discussed in conferences, for example. And we looked at what happens 1 year before the treatment. So we assumed that the treatment is 1 year earlier. And we can see that the results further support that there is an effect of data and code availability policies on strong overstated reporting errors. For strong understated reporting errors, there's a bit mixed evidence. It's interesting to see that there might be something happening actually for non-main tests. So actually understated errors, which might be maybe reflecting sloppiness, might happen more in non-main tests, so in control variables. And data and code policy may help to actually clean this up. Okay, coming to the end. So what we conducted here is a large-scale assessment of reporting errors in economics. We have 3,700 articles and more than 500,000 of tests from the top 50 economic journals. We find very similar to other disciplines that reporting errors are prevalent in economics. 15% of the articles contain at least one strong error in the main tests, and roughly 31% have a strong reporting error somewhere in the paper. And we find some indication for systematic bias towards statistically significant reporting errors. So overstated strong reporting errors are more prevalent than understated strong reporting errors. And with regard to our hypothesis, I didn't say this actually, so I can say it now. We find in the pre-registered analysis no indication that top 5 journals are actually related to strong reporting errors. But in our pre-registration, what we did is we specified that we select control variables by double lasso, and we put in the mix of controls the Scimago journal rank. And of course, the Scimago journal rank is also something that reflects prestige. And so basically what we tested in the pre-registered analysis is whether there is a top 5 effect beyond the Scimago journal rank. And we didn't find this. But actually, when we remove the Scimago journal rank from the regression, there is actually indication that in top 5 journals, there are more strong overstated reporting errors. And then we find indication that open data and code policies may actually help to reduce the prevalence of strong overstated reporting errors, while this is less clear or more ambiguous for the understating reporting errors. So with DORIS, what we currently do is we implement DORIS at betterpapers.org. So the idea, and this is ongoing, so it's not finished yet, the idea is to to provide this tool for authors and reviewers in economics. So basically, everybody can then put his or her paper on the web page, and then it shows where potential reporting errors are. I think this can be very helpful for authors, but also for reviewers. And then one can use this to resolve the reporting errors. Okay, thank you very much.